All right, next one. Would the pH increase or decrease with each of the following additions and why? So we're going to take an acetate buffer here. So acetate is the conjugate base of acetic acid. And we're going to add some sodium hydroxide. Sodium hydroxide, that's our source of OH minus, or hydroxide ion, right? Now if I'm adding a strong base to this acetic acid acetate buffer, my HA form here, that's going to be the acetic acid. I'm going to neutralize that addition. As we've been talking about, we're going to make some water. We're also going to make some CH3COO minus. That's acetate, that's our conjugate base. Now we've learned the Henderson-Hasselbalch equation. It's very useful for predicting the pH of buffered solutions. We said that the pH of a buffered solution can be given by the pKa of the acid form plus the log of the ratio between the molarities or molar concentrations of the base form divided by the acid form. So what's going to happen in this case? Well, in part A, we're going to add a few drops of 0.1 molar NaOH to a considerable amount of this acetate buffer. We're probably not going to exceed the buffering capacity. I mean, we could do a calculation if we really wanted to prove that. Turns out there's usually about 20 drops in 1 milliliter. And we're only adding 5, so we're about, 0.25 milliliters? It's not very much, is it? So I don't think we're going to add enough sodium hydroxide to overcome the buffering capacity of this system, all right? But it's a good idea just to kind of rationalize that and think about it some. But that doesn't mean that we're not going to change anything. In fact, by adding the sodium hydroxide, we are going to change things. We're going to add some hydroxide, and that's going to titrate some of our acid. So as a result, the number in the denominator down the bottom of this fraction will what? It'll decrease. While the number in the numerator of this fraction is going to increase because, well, aren't we making some conjugate base as a result of this titration? We are. So in general, the ratio on the far right will experience a significant increase in magnitude, won't it? When we add the hydroxide. So what that's going to do for us is it's going to make this term bigger on the far right. We're going to add a larger number to the pKa, and the pH will rise. So when we add this 5 drops of a strong base, the pH will go up some. Now let's talk about just briefly the magnitude of the pH change. Is it going to change a lot, or is it going to change a little bit? Well, since we have not overcome the buffering capacity of the system, the pH will change, but it's only going to be a slight change. Not going to change a lot, and that's because the system is still buffered, okay? Very, very similar type of situation in part B. So let's shift gears to part B. Part B, I think we're adding an acid though. We're not adding the base anymore. And that's a significant difference that we need to talk about. Indeed, part B, we are going to add 0.1 molar HCl, which is a source of H+. We're going to add this to our acetate buffer. So what chemistry will occur? Well, there, our acetate, our conjugate base, will neutralize the addition of the H+ from the strong acid. And here we are going to make acetic acid. So acetic acid, all right? And chloride's going to kind of come along for the ride. I didn't show that over here. I guess I should show HCl dissociated, and chloride just kind of comes along for the ride, right? But this is the key crucial reaction. Now, again, think about pH of the solution and the response of the pH in terms of that HH equation. Always go back to that, right? To rationalize changes. These two concentrations on this term on the far right. It's really important, right? What's the concentration of the acid and the base? So in this case, it looks like we're using up some of this conjugate base, the acetate. So this number in the numerator will go down, and in the meantime we're making the acid, so the number in the denominator will increase. So this ratio will become smaller as a result of this reaction. And if that occurs, the pH will drop. And it stands to reason. If you add a strong acid to this solution, the pH should go down a little bit. Now again, we need to consider the magnitude of the change. It's going to be a huge change or just a small change. And I'm going to argue that it's just going to be a small change. And the reason why is because we're adding a very small amount of our HCl to a buffered solution that has a lot of the conjugate acid base present. So in terms of this problem being thought of as a limiting reagent problem, you have a lot of this conjugate base present, and you just have a little bit of this H+. So you can titrate off the H+, get rid of it all, sequester it away in the form of the weak acid, and as a result, you use up a little bit of the acetate, but there's still a lot left. And we've basically offset this change of H+. That's, again, how the buffers work. But the pH will go down a little bit because this ratio of the acid to base will change ever so slightly. Okay? All right, so that's part B. Let's see, moving on to part C. In part C, we're still going to use 5 drops of sodium hydroxide. But here we're going to add it to 0.5 molar HCl. How is this one different, and how would we tackle it? Think about it just for a second. I think it's important for you to think about. So first off here, do we have a buffered solution? That might give us a little bit of a hint. I would argue that we don't. Reason why, can you make a buffer out of a strong acid? Nope, you can't. And HCl is a strong acid. So this will not be a buffered solution. But we do have 100 milliliters, or 0.1 liters of our HCl. And that HCl is half a mole per liter. Okay? So I can compute the moles of HCl present in that sample if I want to. Remember, molarity times volume in liters is moles. So it looks to me like I've got 0.05 mole of HCl present here in part C. Now I already said that about 20 drops is 1 milliliter. So if I'm only using 5, that's about a quarter of a milliliter. Rough estimate, right? So in this case, I could do a quarter of a milliliter, which is 0.00025 liters, if I convert it to liters. And I'm going to multiply that by 0.1. I can compute how many moles of this material I've got. This is my base, right? Not really any problems. So 0.1, oh, I can do that. 0.0000025 mole of OH. That's how much we've got of that, right? So which is bigger? And why is that important? Well, it looks like I've got much more HCl, don't I? And why is that important? Well, what's going to happen here is I'm going to take my HCl and I'm going to react it with my sodium hydroxide. This is a strong acid-base reaction. It proceeds to completion to make water. In this case, some salt, NaCl. This is the chemical basis for the change in this example. But because I have so much more HCl than NaOH, my HCl is by far in excess. Now, how much will be present after the reaction? Well, 0.05. So if I want to compute how many moles are left after the reaction, it will be what? 0.05 minus this number down here at the bottom, 0.000025. I'm running out of space, but you get the idea. This is my moles of my acid. This is my moles of the base. But after this reaction occurs, I'm almost going to have the same amount. I mean, it will change just a little bit. It will decrease, right? So what do we think the net effect of the pH is? And see, the pH is going to rise just a little bit. It's not going to change much. The reason being, I'm still going to have a large excess of my HCl. Now here's the thing. When you're asked questions like this, you always have to estimate quantitatively, in terms of the number of moles of reactants and products, what you've got after the reaction's complete. Here I did that, and I found that I still had a ton of HCl left over. But that won't always be the case. Sometimes you might add enough sodium hydroxide to get to the equivalence point. Sometimes you might add enough sodium hydroxide to get past the equivalence point. My point is that you need to do the math and figure out where you're at on the titration or the curve or the reaction. Okay? And that's an important skill that you'll have to do. For this particular problem, I still have plenty of HCl left to keep the pH very low. Now again, the pH might increase just a little bit, but not very much. It'll still be very acidic, okay? But you got to do the math to figure out where you're at. There's not really any shortcut to doing that. So if you see problems in the homework, if you see problems on the exam, based on this idea where you're actually running a titration, you're actually running a reaction in solution, you got to do the math. You got to work your ICF inventory to figure out where you're at in terms of the amounts or the moles of your reactants and your products. Okay, very, very important. Now there's one more part to this question I want to talk about, is D. In D, we're going to add 5 drops of 0.1 mole per liter NaOH, not to a buffered solution, not to an acid solution, but distilled water. Now, distilled water, does it have any buffering capacity? Nope, it has none. So if you add H plus to distilled water, or you add OH minus to distilled water, you're going to directly affect the equilibrium of water's autoionization or dissociation into ions. You directly impact that. Water has no ability to offset the change of adding a small amount of acid or base. Okay, so when we add this 5 drops of hydroxide ion, what that's going to do is it's going to create a massive and immediate increase in the concentration of hydroxide in that solution. So because of that, the pH will skyrocket. It will change several units, probably at pH 11, pH 12, because water has absolutely no buffering capability whatsoever. All right? So read the question carefully. Know whether you're dealing in a buffer, an acid solution, or just water. Okay? And then make sense of it. And this really all goes back to this idea of solution stoichiometry and being able to compute the number of moles of a solute by doing molarity times volume in liters. That's an important equation. And then the only other thing that you need to know to get this problem right, I think, and make sense of it, is the reactions between a strong acid and strong base, and the reactions in a buffered system. And if you can write those reactions, you should be golden.